Okay, so what we're doing this time is same code that we had last time, but changing sampling from a uniform to a normal distribution in order to generate a random normal variable. We simply need R norm, first values, number of samples that we are generating, number of observations, followed by the mean, standard deviation. I'm picking 3 because my states are 1 through 5. I'm rounding because I want discrete states. And if by chance I go out of my states that I have, I'm going to set it to the minimum or the maximum. So if I exceed 5, I'll say the proposed value is 5. Go below 1, the proposed state is going to be 1. The rest will remain the same. You can't change that, that will change the algorithm. So that's the walk we have. And completely different from the last one, yes. What can you see?
Very 3-oriented.
Very 3-oriented. There are lots of 3s in this example. Why say it?
Because that has the highest chance of just being the theta p.
Right, I'm proposing a lot of 3s because, why 3 then?
Well, because of the normal distribution.
Because it's a normal, because the mean is 3 for a normal distribution is centered at 3, so I'm going to get more 3s than anything else. So, which is why I'm repeatedly getting 3s in terms of proportions. The histogram has a high value for 3. Now, the histogram, okay. So perhaps we might be cheating here because in our target distribution, I kept 3 to be the highest step. Highest density. If you go back up, it was 2, 4, 8, 1, 3. Yes. So let's run the entire code with the normal distribution, and you can see that the target and the estimated probabilities are not the same. Yes. If I kind of move away from state 3 and make the one with density that is the highest to be state 5, the histogram that I would have for the target distribution is completely garbage. Yes. So by all means, what I did in the previous code by setting P of 3 to be 8 is some kind of cheating, because I made R norm to be centered at 3, and I made sure that the highest probability happened at 3. So, which is why it sort of matched, but in reality, was the algorithm doing it right? No, it wasn't. So that is our estimated target distribution. And clearly, that is not what we want. Yes? So it's a complete mess. So what is the lesson that we have to learn from this? It is that the proposals should somehow be meaningful when we simulate and take the walk. If I randomly make arbitrary proposals, then it is not going to help us reach the target distribution. I can change this to 50,000 iterations. Source still wouldn't change. Good. We use a normal distribution if the parameter space is continuous. So does it mean that we can't use Metropolis algorithm for a discrete parameter space? Not true. We can. We just have to use like a discrete distribution to achieve that. Good. So